One of the main benefits of Zephyr is that it comes prepackaged with a number of libraries, including networking stacks, that will work with the supported platforms, assuming you have the required hardware. When it comes to networking and IoT, that means being able to write cross-platform application code that just works across a variety of platforms and architectures. In this episode, we dive into basic networking features to get you started creating IoT devices. I'll show you how to enable the Wi-Fi driver on the ESP32 and create a simple HTTP GET request. Networking is a huge field that we won't have time to really get into. But with our foundation of CMake, Kconfig, and the Devicetree, we can create a simple cross-platform application that performs a simple HTTP GET operation. To create our Wi-Fi demo, we're going to look at several examples, and it's going to be a combination of these examples. So in the Zephyr installation folder, let's go into samples. Let's take a look at net. That's where they keep a lot of their networking examples. And under Wi-Fi, this is an interesting one because if you go look at source, there's like nothing here. This example simply fires up a console or a terminal where you can do things like scan for SSIDs, connect, and do some basic pinging. It's not really a end-to-end Wi-Fi example, but it's useful to test Wi-Fi on your board just to make sure it's working before you do things like HTTP operations. If we look at prj.conf, you can see some of the project settings here, and we're going to be pulling from a lot of these to make our example happen. You'll notice that our board doesn't show up in the boards directory, but the Espressif folks put it in SOC because the example works across a variety of boards and it's dependent on the SoC for the ESP32. In this case, we're using the S3. So take a look at the prj.conf. You notice there is no app CPU here. This is the CPU that's supposed to be running all the networking stuff anyway. We're going to need these settings as well. We turn on Wi-Fi, which seems pretty generic, but then we also have to enable things that are specific to the ESP32. If you look at the overlay, it's actually pretty simple for the ESP32. We're just setting Wi-Fi status OK, and the ESP32 drivers handle the rest of that. If you take a look at the README that's in here, they show you an example of how to use this console. Feel free to mess around with this. You just load this example in and you can do things like Wi-Fi scan and you can try to connect to it. But rather than showing you an interactive console like this, I'd rather show you a basic HTTP GET because I imagine that's what you would be wanting to base your IoT device on, whether it's a REST API or it's something a little more complex like MQTT, but this should get you started going down that route. Back in samples, you can also look in, we're in net and go to sockets. This is where we're gonna find our classic HTTP GET. There's other stuff in here if you wanna take a look, like running your own server, doing echoes, pings, and all of that good stuff. If you look in prj.conf, you can see that this is similar to the Wi-Fi demo, but it uses a static IP address, specifically IPv4. We want to use DHCP. Most home routers are set up for DHCP, so we want to connect Wi-Fi to our router, let it assign us an IP address, and then go from there to make our HTTP request. If you go into source, take a look at httpget.c. This example works with Transport Layer Security, or TLS. It's a protocol to secure communications to and from the server. Most websites enforce it nowadays, so once you get the basic HTTP GET example working, I recommend coming back to this example to work with TLS if you want to, or jump to something like MQTT, which does offer other layers of security. If you scroll through this example, you can see where it puts together a GET request. It gets the address of the host. In this case, it's pointing to google.com. And this performs a DNS lookup so that you can get the IP address in order to make your GET request. If you come down here, you'll notice where it creates a socket. It then connects that socket to the IP address that we got from that DNS request, and then it sends the GET request that was constructed. Finally, it waits, and then anything it receives, it prints to the console. We're going to make our example very similar to this. In fact, we're going to be using more or less this example, but we're going to use Wi-Fi to make it happen. We're going to use DHCP, and we're going to get rid of the stuff for TLS to keep this very, very simple and just pull in a web page from example.com. But once you get that working, like I mentioned, come back to this to figure out how to do TLS or jump to something like MQTT. If you've ever worked with Linux or Unix doing any sort of networking, you've probably come across these socket, connect, send, receive. This is a very common networking API that's part of the POSIX spec. POSIX, or the Portable Operating System Interface, gained life around 1988. This was part of an IEEE standard, and you've probably seen it covering things like pipes and threads, but there's also a networking interface that is commonly used in a lot of C code, especially for things like Unix and Linux, probably Mac OS as well, because that's BSD based. The POSIX networking interface is based around this idea of sockets. So you would create a socket, you would connect to a server or something else on your network. You can send, which is in the S's here, and you can receive. And there's others where you can listen. Say if you're running a server, you can listen for incoming connections. And this interface fully defines everything you might need to do with something like TCP/IP. So we're going to rely on something like this to do our HTTP request. If you come over to the Zephyr documentation, you will find how that's implemented. The reality is that while Zephyr has wrappers, so you can call close, connect, receive, send, like we just saw in that example, all those are wrappers for this interface here that's unique to Zephyr, and that is zsock_something. And then this is where the POSIX API starts. And this is the POSIX call here, so socket, connect, listen, accept, send. But they all have this zsock_. I'm assuming that's Zephyr socket API, and then the function you want to call. In my experience, the POSIX wrapper, so just socket, send, receive, had some issues on the ESP32. So in our example, rather than using that POSIX wrapper, we're going to use these Zephyr-specific zsock functions. The final example we're going to rely on that we're going to combine into our demo is this Zephyr Wi-Fi demo that Craig Peacock put together on GitHub. This gives a great example of how to configure the ESP32 along with a good configuration file. You can see that they specified the heap here. From my experience, you need a good amount of heap. This is like 64 kilobytes of heap in order to avoid having the ESP32 crash, because it just needs a lot of memory to handle Wi-Fi. There's another board on here, the NRF 7002. And if you go into source, you can see there's a good number of files here. We're just going to combine them. So the HTTP GET, we're going to rewrite these and do everything in main. We're not going to implement ping, but feel free to try it if you want to. The wifi.c is where their main is. We're going to simplify this in order to connect to Wi-Fi and then perform a very simple HTTP GET. The important thing here to note is that they are registering callbacks. They're using Wi-Fi management and this net management API to do that. So if you go through the Zephyr documentation, you can find the Wi-Fi management, this header file, that allows us to do things like configure Wi-Fi and create these callbacks. There's a bunch of status information here as well. We're going to use that to connect to Wi-Fi. And there's also net management. Wi-Fi.h includes netmanagement.h. So this is specific to Wi-Fi stuff. If you go into the net management, here's the netmanagement.h. Here's the reference for that. This is what actually does all the registering. I'm assuming it's a common interface for various different types of networking, such as Ethernet, in addition to things like Wi-Fi. With that in mind, let's go ahead and start creating our demo. Let's get out of samples, go into workspace, go into apps, and let's create a new folder called 11 demo Wi-Fi. In there, let's start by making our CMake lists. The first few lines are going to be our normal CMake lists, where we set the minimum required version, we find the Zephyr package to extend CMake functionality, and we define our project or set the name to demo Wi-Fi. The only thing we're going to do differently here is we're actually going to create a few more source files in our source directory beyond just the simple main.c, because we want to keep some of them abstracted away, like handling Wi-Fi. Rather than specifying target sources manually, which you could do, you could specify the individual files. We could also use this glob functionality or file within CMake that creates a glob, which is just a collection of files and paths. We're going to create this glob name as app sources, and we're going to say all of the .c files within the source directory are part of this glob. Then we're going to add all of those sources by using that app sources variable in target sources to apply them or add them to the app target. We're doing this instead of manually adding source main.c to the app target. Let's go ahead and save that. Then we want to create our prj.conf file. Note that I'm not going to go through menu config, but you are welcome to. These symbol definitions come from combining and paring down the 3 examples that we looked at. So I recommend using those as your starting point and then seeing how we get to this point with the minimal set of symbols. Something I discovered recently after doing the previous demos, when you do the log output and it tries to color code them with those funky symbols, you can set the log mode minimal symbol to yes to get rid of those color codes. If you're using a fully featured serial terminal where it will accept those color codes, feel free to set this to no or don't include this symbol at all. But because we're using a very simple monochrome one, this helps make it more readable. If you ever find your ESP32 randomly crashing, in many cases it's because you don't have enough memory allocated to the main stack or the stack for your main thread. Simply increase that value to get more memory to avoid those crashes. It's a stack overflow that's occurring, so we're gonna go to 4K because I found it's needed for dealing with Wi-Fi. The Wi-Fi symbol isn't available for all boards, but for the ESP32 it's necessary, and I'm fairly sure that any board that has Wi-Fi, there is a Wi-Fi symbol associated with it, so we're gonna put that in prj.conf rather than in our board configuration. We need to enable the various networking stacks. We first enable the generic networking symbol, and then we enable the individual IP and TCP stacks. We're going to enable IPv4. That's the one we're actually going to use most of the time in this demo. I'm going to show you how to enable IPv6 in case you want to use it, but we're actually going to rely on IPv4 for most of this demo. If you have a router or system that relies and only uses IPv6, then you might have to change some of the code. Just keep that in mind going forward, but I'm going to try to keep it as simple as possible for most people's home networks. We'll also enable TCP, which is necessary for doing HTTP requests because that's built on TCP IP, and then we'll also enable sockets. That allows us to call those POSIX-like functions. We'll also enable DHCP specifically for IPv4. Once again, you might have to change this to v6 if your network is IPv6 only. There's a software package that we saw earlier in those demos that allowed us to do DNS lookups. We will need that if we are trying to do things like HTTP requests. So we will enable the DNS resolver. Then we'll configure the networking timeout. In this case, I'm going to set it to 30 seconds because it might take a while to get an IP address from your router or DHCP server. If you don't configure this, I think it's something pretty low, and you might find that you're timing out very quickly before you get an IP address. So increase this to something larger, like 30 seconds. The networking library in Zephyr has its own logging system, so it's a good idea to enable that if you want to see the output. Of course, on deployment, for a real product, you probably want to disable this. And that's the advantage of having multiple configuration files where you can switch between your debugging and development or your deployment options. In my experience with the ESP32, you have to enable this L2 Ethernet option to get Wi-Fi to work. I'm assuming it's an underlying layer. And my guess is it's not unique to the ESP32, so we'll just say it's required for Wi-Fi. If I'm off on that and you happen to know it works on other boards or it's not required for other boards, let me know in the comments. And that's where I'm going to stop for PRJ. Let's make our boards folder. We'll start with our device tree here with our overlay file. In the ESP32, this is pre-configured for us, so we just have to enable it by setting the status property in the Wi-Fi node to OK. Save that. And we'll create our board-specific configuration file. I found that there's this tricky symbol you have to enable called ESP32 Wi-Fi STA mode auto DHCP v4, I guess as opposed to v6, so you'd have to enable v6 there if you're using that. You have to enable this if you want to actually get an IP address from your DHCP server or your router. I found that you have to enable the system heap for Wi-Fi on the ESP32 and set it to some rather large value, like 50K, to make that happen. Otherwise, you will find that Wi-Fi just kind of crashes on the ESP32. And we finally get to write our source code. So in here, we're going to start with our Wi-Fi library, a sort of driver that wraps up the Zephyr function so we can keep our main simple. Let's create wifi.h. This will declare our functions. We'll put our standard header guard. Then we'll define 3 basic functions here. Wi-Fi init just initializes the underlying hardware. We're going to call connect to connect to our SSID with a pre-shared key or PSK. Note that this is a very simple way to do this. I'm not trying to hash or make the password very secure. We're just going to use this as an example on how you might do this. Right now, we're just going to store our password in plain text in the C file, but feel free to find other ways to secure that password. Maybe you provision the device via Bluetooth if you're trying to create a final product. Then we will create this very simple Wi-Fi wait for IP address. We are just assuming we're using DHCP here, and we're going to wait for an IP address from the router or DHCP server, and this is going to be a blocking function. It's just going to wait for that to occur. Like I mentioned, we're trying to do things in the simplest way possible, rather than say the more programmatically correct or efficient way to do this, say in a different thread with correct callbacks. But you'll see how the callbacks are used, so you can do that yourself and take this a step further. Let's save that. Let's create a file. We're going to call this wifi.c. We're going to do some basic string manipulation, so we'll need that library, and we'll include the kernel.h, and we also need that Wi-Fi management.h file that we saw earlier that allows us to do a lot of the networking configuration through Wi-Fi. We're going to define two different callbacks, one for Wi-Fi events that might occur, and one for IPv4 events. In this case, it's we receive an IPv4 address from our DHCP server. Because Zephyr likes to be thread safe in everything, it's actually a very good underlying RTOS. It wants us to use things like semaphores to notify when these events occur, and this is very useful for having multiple threads running to do things like handling your networking stack. In fact, on the ESP32, you have two separate CPU cores. Generally, one of the CPU cores is used to handle things like networking, Bluetooth, and Wi-Fi. The other is for your application, and you would communicate through things like semaphores or queues, so that your application knows when Wi-Fi things have happened, such as you connect to a Wi-Fi or you get a response from a server. So to use the Zephyr system, we're going to create these two semaphores, and we're going to use them in a very simple manner. In fact, we're going to create blocking functions that just wait for these semaphores. It's not the best way to do it, but it allows you to see how to do this, and with a very simple application. Notice that these callbacks and semaphores are static, so they are unique to this wifi.c file. You can't access them outside of this file. As you've seen before with other callback events, Zephyr defines the signature that we have to use. So we're going to create our own callback here called onWiFi event. It's going to follow the signature that Zephyr expects for these net management events. It's going to pass in the callback so we can get some information from that. The event that has occurred, it's an ID. It's just a simple unsigned integer. And the interface where this event occurred for our ESP32, that should be the Wi-Fi interface. We can pull the info from the callback event. That's just going to be the status of what occurred. Then we're going to take a look at that net management event, which is just going to be a number, and compare it to a number of potential results that Zephyr has defined for us. In this case, if that event number is the net event Wi-Fi connect result, we know that we are getting called from a connection event. We're going to see if the status is basically okay. If it's not 0, then something failed, so we will print that status and say we couldn't connect. Otherwise, if it is 0, then we know we've connected, so we'll say we're connected and then return that semaphore or notify the system that the connection has occurred so that the things waiting for this connection can start running, for example, say getting an IP address or continuing along with our application code. If the callback occurred because of a disconnect event, we will check that status and print if the disconnect did not work, or say we are disconnected and go ahead and take that Wi-Fi semaphore. That semaphore is used to notify the system if we are connected to Wi-Fi or not, rather than say a global flag, but that would probably also work. Just make sure you would protect it with something like a mutex if you're running this in a multi-threaded environment. Next, we have the event handler for Wi-Fi management, in this case, the IPv4. We get that from the DHCP server. This is that other semaphore we created, or the other callback we defined. The net management system can call this, and so we know that we have received an IP address from the router or the DHCP server. All we're going to do, assuming that the event is the IPv4 address has been obtained, we will give that semaphore up to notify the system that we have now an IPv4 address. Note that you will need to modify this if you're using IPv6. You will have to look for that IPv6 net event and maybe create a separate semaphore for that. But like I said, I removed those to keep this very simple so you can see what's going on. In our public-facing Wi-Fi init function, we're going to initialize the callbacks. In fact, that's all this initialization function is going to do. The first one we're going to initialize is the Wi-Fi callback. We're going to use the built-in net management initialize event callback function defined by Zephyr. We're going to pass it in the address of that callback struct where Zephyr keeps all that information and the name of the function, in this case, the onWiFi connection event. We'll also define the events that can occur to trigger this callback. In this case, it's the net event Wi-Fi connect result and the disconnect result. We're going to OR those together because each one is a flag in that unsigned 32-bit integer. If you scroll up here, these are the two events that the callback can be triggered on. Here's the connection result, here's the disconnection result, and we just look at the event to figure out which of those events have occurred. We're going to initialize another callback, and this one, the other one we wrote, which is the IPv4 callback. That's when the address has been obtained from the DHCP server, and the only event that can trigger that is that we've obtained an IPv4 address. Once again, feel free to change this to IPv6 if that's what you're working with. In addition to initializing the event callbacks, we actually need to add them or say that they are ready to be used. We use the net management add event callback function to do that, and we pass in the structs of the two callbacks we defined. Next, we're going to define our public-facing Wi-Fi connect event. This is blocking. We're going to try to keep this as simple as possible so you can see how to use it in your application. Feel free to change this to make it nice and multi-threaded. We'll define some variables for us to use, a return value, the networking interface, and the Wi-Fi connection request parameters that we'll fill out to make that connection request. We're going to get the default interface from Zephyr using this net if or interface get default. For the ESP32, once we've set it all up, this should be the Wi-Fi interface. If you're using another board, this might be a little different, so keep that in mind. If you're using something else, then you might have to specify exactly which interface you want to work with, whether that's an Ethernet or one of several Wi-Fi interfaces. Then we'll fill in the connection request parameters. This is where you actually assign the things like the SSID and the password. Note that it wants to convert these obvious strings to unsigned 8-bit integers, so we will cast that pointer. It also wants the length, so we're going to use the very common string length function in the string library to make that happen. We'll do the same thing with the PSK or pre-shared key, and we will set the security to PSK. This is where you can do things like hashing the pre-shared key if you don't want to save it in plain text on your device. Zephyr also supports WPA3, which I'm not using here, so if you're enforcing that in your network, you might have to change that. And there's other security measures you could take here if you want to protect that key and your network password. We're going to set the frequency band to unknown and let it figure it out with the router. And we can also define the available channels here that it will connect to. Once again, we'll just say any. That allows it to negotiate with the router and just let it connect to whatever channel the router wants to use. MFP is the management frame protection. It's defined apparently in 802.11w. I honestly don't know a lot about it, but it does seem if we set it to optional, it can figure it out with the router. Now that we have everything configured, we'll create the request. We're just going to use this net management function. We will set the request to the Wi-Fi connect request, set our interface, which we got earlier, set our params, which we set up, and it wants the size of those parameters, so we'll just dynamically find that and send that in as a parameter. In an attempt to make this very simple, here's where we're going to actually block the function by waiting for the Wi-Fi semaphore to become available. That means we have a definite connection to our router before continuing and returning to the caller. Rather than multi-threading and waiting for an IP address and having callbacks, we're just going to create a very simple function that blocks until we get an IP address from our DHCP server. We'll create some variables here for us to use. We'll have the status for our interface, a pointer to our interface, a string for our IP address. In this case, we'll use IPv4 address, so feel free to change that to 6 if you need the longer address, and the address of the gateway. As before, we'll get the default interface, which should be Wi-Fi for our ESP32. What's interesting here is that with most home routers, they come with DHCP enabled by default, and they assume you're using DHCP, which just hands out the IP addresses. So all we need to do is connect to the router and just let it give us an IP address. Zephyr handles that on the back end. So we're just going to have that callback event waiting for when the router attempts to give us an IP address. And all that's going to do is just notify this main thread that the IPv4 address has been obtained. Once again, you might need to change this to v6 if you're working with IPv6 addresses. And then we'll use this net management function to make a request to get the status of the Wi-Fi. Now that we have obtained an IP address, we'll pass in the interface, the status we want to have filled out for us, and the size of that status struct. If that doesn't work, in other words, if it returns something other than 0, we'll just print that we couldn't get the Wi-Fi status. Next, we'll get the IP address that's been assigned to us. We'll use this function net address n2p. I honestly do not know what that n2p stands for. The Zephyr documentation doesn't really tell me here, but it allows us to pass in the struct for an IPv4 or IPv6 address, and it gives it to us in string format, which we will store in this character array IP address. I'll move the curly braces around so it lines up with the normal convention. We'll use the same function again to get the IP address of the gateway. In this case, our router. We'll first set that string to 0 just to make sure it's cleared out. Then we'll use that net address n2p to do the same thing. Notice that we're digging pretty deep into this interface struct. That struct holds a lot of information about our Wi-Fi interface. We go to config IP IPv4 and get the gateway address that's been assigned here. Once we have all that information, we will print out the full Wi-Fi status, mostly so you can see how to obtain this information should you need it in your own code. We can check status.state to see if we are associated or connected to a gateway or router. We will print the SSID, the band. We will also print the channel, the security that we're using. In addition, we will print our own IP address and the IP address of the gateway. Finally, we will offer a public-facing function to disconnect from the Wi-Fi network. And I totally forgot to add that here in our header file. In fact, we should actually return an integer rather than void. And then in our library code, we will define that function. And like I said, I wanted integer because we're going to return that code. In that function, we will define a couple of variables. Specifically, we're going to get a pointer to that network interface. We'll use the get default, so it should be Wi-Fi, and we'll define a return code. And all we're going to do is just call that net management with the Wi-Fi disconnect request. We will give it to the interface, should be Wi-Fi, and we will give it no other parameters, so that's a size of 0. We will return that return code and let the caller deal with any errors. Let's save that, and with that, we should be ready for our application code. In source, let's create a new file. We're going to call it main.c, as we usually do, and let's include some header files. We'll include standard input-output like we usually do. We'll want to do some string manipulation. We will need the Zephyr kernel, like we almost always do, and we will want to include the networking socket library so we can use those zsock functions. Let's also include the header file that is in the same directory that allows us to call those Wi-Fi functions that we just created. And here's where you define your Wi-Fi SSID and password to connect to your particular network. So change my SSID and my password to the Wi-Fi access point name or your SSID for your network and your particular password. Then we'll define our settings for the HTTP GET request. In this case, we're just going to get the main page from example.com. So the host is example.com. We'll do a DNS lookup on that to get the IP address, and then the uniform resource locator or URL for the item or file on that host or on that server. In this case, it's just the home page, which should redirect to index.html. So we're just going to fetch example.com/index.html. We'll also want to create a global here that is the response. This is just a pretty large buffer that our socket system is just going to dump the received characters into when it receives a response from the server. In this case, it's going to be that HTML page. I'm going to borrow this function from that GitHub repo example we looked at. This just prints out the IP address results from a DNS lookup. You don't necessarily have to have this, but it is very useful if you want to see, hey, did that DNS work and what is that IP address? The first two variables are the IP address strings for IPv4 and IPv6. I'm going to demonstrate IPv6 support here, even if we're not using it in our main code. Then we'll define some socket address structs to hold our information in so that we can print them out. Note that when we do a DNS lookup, it is possible to get more than one result. So we have to iterate over those results and print all of the possible addresses. In most cases, you're going to get one address. It seems that the results parameter, in this case, the zsock address info struct, is an iterable, so we can call the next function on it to go through all of the possible results until we hit a null result, which means we've hit the end of that list, much like you would see in like Python or other type of iterables. If the address family is IPv4, we are going to get the address from that result. In fact, this needs to be AF for that family type. Then we will call the zsock inet n2p function. And I did look it up. N2p is Internet Network to Presentation. This allows us to convert things like addresses to strings. We'll give it the type, AF inet, in this case basically says IPv4. We'll give it the address and where we want to store it. In this case, we're storing the string in our IPv4 variable. And we need to pass in that string length. With that information, we're just going to print it to the console for now, but feel free to use it however you wish in your code. And if the family of the address is IPv6, we are going to get that address, cast it to a sock address that we then convert to a string, much like we did before, but we're doing it with IPv6, and we just print that address to the console. Next, we'll define our main function. In it, we'll start with some variables. First, we'll have some hints, which is used to help the DNS lookup. We'll have the result, which is where the DNS lookup stores its results, and we'll use the address in there to connect with our socket. We will have a string to store our HTTP request. we will have a socket ID, that's just an integer. The length, receive total, and return functions are all just integers we'll use throughout this application. We'll say hello by printing something to the console. We'll initialize Wi-Fi. Remember, this is the function we wrote earlier in our little Wi-Fi wrapper. Then we'll call our Wi-Fi connect function that we wrote. We'll pass it in the SSID and password that we set. If there's an error, we'll check that and print it to the console and get out of this function, basically crashing our application. Note that Wi-Fi connect is blocking. In addition, we will wait to receive an IP address from our DHCP server. This is also blocking. There are better and more efficient ways to do this, but in the interest of keeping this simple, we will wait for the ESP32 to connect to our router and get that IP address. Next, we will construct our HTTP request. We're just going to create a string to do this, and that string is going to be stored in that HTTP request buffer that we created. We will write out the string. This is the real simple request. We're going to say get the URL, so index.html. The server is going to figure that out for us. We're going to use HTTP version 1.1, new line, host, and we're going to say example.com. We define those above in our macros. When we do a DNS lookup, we can offer these hints to basically say, hey, we want an IPv4 address rather than IPv6, and we're going to create a TCP socket, and that helps the DNS request figure out what kind of information to give back to us. Next, we're going to print to the console that we are doing a DNS lookup, and we're going to use this handy zsock get address info that does the DNS lookup. We're going to give it the host, which port we want to use, in this case 80. Notice if you're doing TLS, this will probably be a different port. We're going to provide the hints that we filled out earlier, and we're going to provide a pointer to the result struct that the DNS request, in theory, should fill out for us. If there's any errors with that lookup, we will print that to the screen, and we will call the function we wrote earlier at the top of this main.c to print out the results of that DNS lookup. In other words, which IP address did we get from that? At this point, we are ready to create our HTTP request. To do that, we're going to use that POSIX-like interface that Zephyr provides to create a socket, connect a socket, send the request, and then print out whatever we receive on that socket. And then don't forget to close the socket when you're done. We'll create a socket with socket, or in this case, zsock_socket, by passing in the family, socket type, and protocol that was filled out in that DNS request. Hence, that result struct is being used here, and we're getting the fields from that to create this new socket, because that's what we're going to use to communicate with that particular server. Notice that the POSIX networking return types work a little differently than what you might be used to for other functions in Zephyr. In this creation of a new socket, it will return the socket ID that we can use to interact with the socket later. If that is some negative value, usually something like -1, that means the socket was not created and there was an error. We're not going to print that error code because it's not the same as a Zephyr error code. There is a global variable called errno, or error number, that is set within this POSIX interface. We can read that and look up the error code, which will help us debug any issues we might have with these POSIX-style functions. It's a little confusing. I much prefer the error code that's returned directly, but this is what POSIX uses, and it's been doing so since, I don't know, the 80s or 90s. And Zephyr is doing the same thing because of that legacy. We'll send the request, but before we do that, I forgot to write out the connection part, because it's create the socket, connect the socket, send the request. But just so you see, we're going to print send HTTP request. We're going to send our HTTP request, that's the string that we created earlier, and then we will print out any error codes if that did not go through. But let's go above that, because we need to connect the socket first. So to connect the socket, we'll use that POSIX-style interface, zsock_connect. We will give it the socket, in this case it's the socket ID, or that number. We'll also provide it with the address we got from that DNS lookup and the length of that address. After we've connected it, we will go ahead and send the HTTP request, and then we will wait and print the response. I'll print something to the console with an extra line so it helps separate that response we're about to get. I'll also keep a running total of the bytes we received, just so you can see how that works if you need to, say, dynamically allocate some memory. And in a while forever loop, we're just going to continuously receive from that socket until the server terminates that connection or says, I'm done giving you data. In this while loop, we will start off by receiving data by calling this POSIX-style receive function. We'll give it that socket ID, which is sock for us, and we will give it response, which is that buffer we set up, that global buffer we set up. We'll also give it the size of that response. Notice we give it the size of response -1 because we always want that last byte reserved to be the null character, or 0. Otherwise, we might run into issues trying to print stuff to the screen. If the length returned is less than 0, it means we have an error. We'll print that error number to the screen, and I should have done this earlier, but there is a handy string error function built in that we can pass it the error number, and it will print out the string associated with that error. You could also just look it up on the internet if you want to. If the length comes back as 0, it means the server is done sending us data so we can exit out of this loop. The reason we're doing this in a loop is because that response buffer that we created is only 512 bytes. We might be limited, especially on an embedded system, by the amount of data we can store at a time. You'll run into this if you try to, say, download rather large web pages and it's lots of HTML and you need like a megabyte and your embedded system just doesn't have that much RAM. So we can buffer chunks at a time. In this case, we'll print those chunks to the screen and then go back to the beginning of that while loop while we still have chunks in waiting. We will receive those and print those. When we're done receiving all the chunks, we will just end and break out of this loop and close the socket. Remember how earlier that we set the size of the buffer for ZSock to be 1 less than the size of the actual buffer? Here's where we're going to set the final character at the end of that chunk to be 0, so we have a null terminated string, and we can print that to the console. Each time through the loop, we're going to have a running total of the number of bytes received, and we're going to print that to the console after we print out that web page. Every good client should close out the socket once they are done using it, so we will call ZSock close and that socket ID. And we will return 0 to say we are done with this application. So on each reset, it's just going to connect to Wi-Fi, get example.com, print it to the console, and then be done. Let's save our work, and we are ready to build. Let's go ahead and create a new terminal in Workspace here. Let's go into Apps. Let's go into 11 Demo Wi-Fi. We're going to say West build. Say always pristine for our build folder, give it the board of our ESP32S3 Dev Kit C with the qualifiers of ESP32S3 and the Pro CPU. We're not doing anything with the app CPU in this course. Then for CMake, we're going to pass in the overlay file that we created along with the extra configuration file that we made to configure Wi-Fi for the ESP32. Let's press enter and hope this builds. It looks like I've got an error because I probably forgot a semicolon somewhere. All right. Good old classic C error. Let's save that and try again. Another error. Oh my goodness, I'm forgetting semicolons everywhere. And we have response undeclared because I'm not sure. Let's see what's going on here. So response is undeclared. That should be a global variable. Did I misspell it? No, it's probably not taking because I didn't have that semicolon. That's pretty classic. All right, try again. Hey, it actually built this time. Let's see if it works. On your host machine, don't forget to activate your virtual environment. And we're going to call python-m ESP tool, fill out the parameters there, and set it to flash the zephyr.bin in the build directory of our demo Wi-Fi. In a minute, that should flash. With that done, open up a serial terminal to your device and wait a moment while it connects and tries to get the web page. So if you see something that looks like HTML, that means it worked. Congratulations, it connected and it sent the request correctly and received and printed it to the console. If you go back up, you can see where Zephyr starts. There's a couple of interesting things here to note. First is that these errors of failed to send packet before we even get an IP address. I am honestly not sure why this is occurring. I've talked to some of the Espressif developer folks for Zephyr. These should be fixed in Zephyr version 4.0, which, interestingly enough, came out while I was recording this. So I'm still going to use version 3.7 for this series, but you're welcome to try version 4.0 to see if that works for you using this code. Note that Zephyr changes quite a bit, so some of the functions might not work anymore because the API changes. You'll also notice that when the DHCP service gives us an IP address, it also tries to send us a number of DNS servers that we can use by default. Apparently the ESP32 can only save a handful of them, or one, and we just don't have room to save any more, which is fine, it still works. We get the IP address, it says connected, and it prints out the status for us. So we are using WPA2. Here's my SSID. We have the IP address that was given to us, so that's the ESP32's IP address. My gateway is 10.0.0.1. We then perform that DNS lookup. Example.com's IP address for IPv4 is this right here. We send off that HTTP request and we print out the response. So it looks like it's working for us. And if you scroll all the way down after that request, you should see the total bytes received. We got close to 1,600 bytes from that server, from example.com. And you can see how we can print it out in chunks, and this should be one long string that we received 511, I believe, bytes at a time, printed those out, and then we can say we actually received this many. This allows you to work in chunks or stream parts of it, even if you don't have a big enough buffer to hold the entire page or response from the server. For your challenge, I want you to essentially repeat what we've done here, but instead of using sockets to send and receive an HTTP request, I would like you to use this HTTP client API in Zephyr to construct the HTTP request, send the request, and then print the results in a callback. If you come down to the functions, you can see there's just one here. It's to make the request. But you create a callback, and that's where you get the response from the server. Note that this is considered a library as part of the networking stack inside of Zephyr that is not POSIX. It is a unique to Zephyr type of library, but it should get you familiar with working with Zephyr libraries to handle some of the things for you. Keep in mind that you will still need to do a DNS lookup so that you can get an IP address, and you still have to connect a socket to pass it into this request. Also, note that because this is a separate library, you will need to enable at least one Kconfig symbol to get this library to build and link to your application. If you would like an example as a hint that you can work from, go to the Zephyr source code, go down to samples, go to net, since we seem to be working a lot in there. If you go into sockets, the HTTP client that we looked at earlier actually uses this. So if you come down here, you can see where it connects the socket, but then it makes the request not using sockets, but using this HTTP client request function. So I recommend using this application as a starting point for your challenge. And as per usual, I will have my solution in the GitHub repo should you want to compare how you did it. I know that we only just scratched the surface. We didn't get into things like Bluetooth, security, and MQTT to name a few. But a simple GET request should give you a good starting point to create networking applications and IoT devices. This wraps up the software demos for this series. I hope that I've given you a good starting point for developing your applications with Zephyr and using CMake, Kconfig, and the Devicetree to configure the hardware. In the final episode, I'll go over the basics of creating a custom board definition so that you can easily port your application to a custom PCB. See you then.